Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone. Let us look at the dislocation superlattices. We have looked at all the dislocation types and energetics and the stress fields and motion, dynamics, mechanics, everything, right? So in that continuation, I just want to cover another aspect of dislocations in superlattice, which is also very important, which I wanted to just add to that lecture. Because I wanted to do it separately because it has some special properties which is not considered in the conventional dislocation, I would say, formulation. Okay, so let us see what is this superlattice dislocations. So if you recall all the ordered systems, typical ones are that the unit cell shown here of B2 and L12 superlattices. Okay, these are all two possible cubic superlattices produced by alloys of composition AB. For example, copper, zinc, and nickel, aluminum, and AB3. For example, Cu3Au and Na3Al, or with crystallographic identifications B2 and L12 respectively. So how they are forming? During nucleation and growth of ordered domains in a disordered crystal, the lattice parameter changes sufficiently small for atomic planes to remain continuous. Okay. So how this is identified then? When the domains meet, the A and B sublattices are either in phase, that is in step with other, or out of phase. The later conditions results in an anti-phase boundary, APB, popularly known as APB. It has characteristic energy because the nearest neighbor coordination of the superlattice is destroyed. Typical energies are similar to those of stacking faults, that is approximately 10 to 100 millijoules per meter squared. So what you have to understand is it is almost similar to the stacking fault energy or surface energy. We have been looking at all these things related to dislocation. So similar ideas are applied here. You can just follow this. Suppose if you look at the slip and dislocations, and there is a nice schematic or I would say that it is very much simplified schematic in order to understand this little complex or confusing reactions here. A two-dimensional schematic of an ordered AB crystal. A and B atoms are preferred near neighbors. So what does it mean? It means for A, the nearest neighbor is B. For a B, the nearest neighbors are A. So that is AB crystal type. Suppose if the slip plane is designated here, slips by a unit distance B, like in a normal lattice along the slip planes, produces undesirable atomic bonding across the plane. So you are seeing this crystal in A, which is going to produce a slip with the magnitude of B here, that is the distance, and then it creates a standard slip. But there is a difference between an ordinary crystal and ordered crystal. Here is by slip it produces an undesirable bond. What is undesirable bond here? Because we said that then the preferred neighbors are A and B atoms, but here it is BB, AA, BB, AA, like that. So the whole across the slip plane. So this is undesirable atomic bonding across the slip plane. Okay. So what? So slip by the moment of a superlattice dislocation with a budget vector 2b does not produce undesirable bonding. Suppose if you look at a schematic here, a 2D lattice, where you see that two edge dislocations are placed side by side, when this kind of dislocation passes through this lattice, then it does not produce undesirable bonds. How? Because one slip produces undesirable bond, the another dislocation which follows will put the lattice back into the order. But what is the difference between a normal Burgers vector and this? A normal Burgers vector will be having the magnitude like B. Here it is 2, so it is a 2B. Burgers vectors are no longer B in the ordered crystal, it is rather 2B. Okay. Because of the elastic repulsion between the individual dislocation in the super dislocation, it splits. You see, we have the background to understand this. The elastic repulsive force between the two edge dislocation will try to keep them away in the partial. Like a unit dislocation will split into Shockley partial, and then the partial will recombine and move, or it will just wide separated and then remain stable. It's completely based upon the stacking fault energy. Similarly, here to keep this, even though it can move as a pair here, the elastic strain energy associated with this is much higher than the normal unit dislocation. So what happens? It splits. Okay, so it splits like this, which is shown in the fourth figure D here. So which is quite interesting. Like the super dislocation with the Burgers vector 2B gets split into two unit dislocations, edge dislocations, leaving behind the antiphase boundary domain. So the two, you can say that it is a two super partials are separated widely. In between you have the antiphase domain band actually. So propagation of the super dislocation as a unit is not accompanied by the formation of poor bonds across the interface. So if this kind of a pair moves, then there is no problem. But yet the elastic strain energy, as I just mentioned, which is 2B squared of super dislocation, is greater than that of two widely separated single dislocations, which is GB squared. So GB squared energy of this is GB squared and GB squared. So it is widely separated here, which is a normal dislocation. But here it is widely separated from the super dislocation, but keeping this antiphase domain in between. Okay. So as a result of this elastic repulsion, the individual dislocations are separated and the improper bonding across the slip plane occurs between them. So the improper bonding across the slip, and it has got a characteristic energy associated with it, that is called antiphase domain energy. That is also we have seen. So in analogy with the partial dislocations, the equilibrium separation of the unit dislocation depends on the value of antiphase boundary energy. So it is something like your stacking fault energy, whether it is going to remain a split Shockley partials or it becomes a unit dislocation. Similarly here, whether it is going to remain as a super dislocation or it's going to split into super partial, which is decided by the antiphase boundary energy and of course the repulsive force. Okay. In crystals such as Cu3Au with the A3B stoichiometry and possessing the FCC cubic structure, the superlattice dislocation is composed of two unit A by 2 110 dislocation. So it is a similar Burgers vector, but it is two units. So that is what is shown here. So if you approach the problem like this, it is very easy to understand. So that's why I brought this schematic. So now we can look at the other aspects. The region across the slip plane over which the APB exists is bounded on both sides by individual stacking faults associated with the dissociation of unit dislocations into partials. So I just showed in the previous schematic where the APB domain is bounded by two individual unit dislocations. Now we are talking about dissociation of two unit dislocations further into partials. So that means you have an APB domain and then both sides, the unit dislocations are decomposed into two Shockley partials. So you are going to have a situation where an APB domain in between, and then by both sides they are bounded by the APB plus stacking fault. Super partials can be there. A stacking fault can be there along with the APB on both sides. So the total width is now considered as a antiphase boundary width. Okay. So what is this? Is what shown here in the schematic. On the slip plane in an ordered A3B crystal, the unit dislocation of superlattice dislocation have split into partials. So the super dislocation has split into partials 1, 2, and 3, 4. Thus, both antiphase and stacking fault boundaries exist across the slip plane. So this is one way of looking at it, what the previous schematic showed, which is shown in the other format, right? To take into all the possible combinations of faults and boundaries. Now we will look at the same idea in the atomistic level. So what is that I'm trying to show here? Here it is, arrangement of atoms in the two adjacent atomic planes in an L12 superlattice. So here you are seeing that completely filled circle, open circle, and then open circle inside the black dot and the open circle inside the blue dot. So these are all A. The first one is A in the plane of the diagram, B in the plane of diagram, and this one A in adjacent plane and B in adjacent plane. So you can now clearly see that. So this is B, A, B, A, B, like that. So A, B, A, B, A, B. Sorry, B, A, something like that. So this is two layers adjacent. That is the dotted line shows the layer which is below the solid line bond. Okay. So what are these? Indicate? They are 111 type of planes. Okay. Similarly, you have 100 type of planes of L12 superlattice. That is nothing but your FCC type of lattice. Okay. What are the points to be noted? Antiphase boundaries are also arise in the core of dislocations in ordered alloys, and this is of considerable technological significance because of their influence on the high temperature mechanical properties of these materials. So this is very important. That's why I just wanted to discuss now itself, so that later we can just simply refer these dislocation activity and then move on with the property and mechanical tests and so on. As the temperature is increased, the CRSS actually increases an effect known as the yield stress anomaly. See, what we have to recall here is we are going to discuss about the critical resolved shear stress that is required for the slip to take place. Okay. In a normal FCC lattice, CRSS is independent of temperature. Okay. But in this superlattice, it is dependent on temperature. As the temperature increases, the CRSS actually increases. That is why it is called yield stress anomaly. If the order disorder transition temperature for the alloy is high enough, the yield stress reaches a peak. So you have to have this condition. You can have this ordered superlattice or the alloy which contains this kind of atomic structure, but their order disorder transition temperature should be high. Then we can exploit this situation to obtain high yield stress as the I would say normally above room temperature, I would say, or any high temperature below this transition temperature. For example, what we are looking at is the nickel-based superalloy, where Ni3Al is the gamma prime phase in the gamma matrix. Okay, so their transition temperature is in the order of 800 to 1000 Kelvin, and then they exhibit these kind of hardening in the application of turbine blades and so on. So it's very important applications. So this is one classical example where this particular idea is completely exploited for the technological advancement. Okay. In ordered state, 1 by 2, 1, 1, 0 vectors are not lattice translation vectors, and so gliding dislocations leave behind a surface of disorder APB. So in a normal FCC, the lattice translation vector is 1 by 2, 1, 1, 0. Okay, but in ordered FCC, 1 by 2, 1, 1, 0 is not a lattice translation vector. That is why if you just move this atom by this magnitude, then it leaves behind the disorder, that is antiphase boundary. The perfect dislocation moving on either the 111 or 100 planes of L12 superlattice consists of two 1 by 2, 110 super partial dislocations joined by an APB. This is exactly we have just demonstrated in the previous slide. This super dislocation has the Burgers vectors 110, which is a lattice translation vector. Okay, so now you have to remember this super dislocation can glide on both 111 as well as 100. Please remember that. The spacing in equilibrium is given by the balance between elastic repulsive force between the two superpartials and the opposing force due to APB energy. So what is going to decide whether these two partials are going to remain like this or they are going to just combine and then move? That depends upon the, in fact, it's the ratio of APB energy over the GB, that is elastic force. Okay, what is that we are now trying to see from this or understand from this diagram now? Suppose since we have already declared that 1 by 2, 110 is not the lattice translation vector. But then just to prove that if you just move this layer, the top layer by this magnitude of 110, then what happens? When you move this layer to this position, then what happens? Instead of, you see AB, AB, AB. Now if you move like this, then it will become AA, BB, AA, BB, like what we have seen in the previous schematic. So that is what it is creating a APB. On the other hand, very interestingly, if you look at, excuse me, if you look at 100 plane and the similar movement of the lattice translation vector, if you move, sorry, it is not lattice translation vector here, but I'm just saying if you move this layer again by 1 by 2, 0, 1, 1 magnitude, then what happens here? There is a difference. If X goes to Y, then the nearest neighbor bonds are not changing in 100. Very, very important. Not like in 111. 111, everything changes. It forms an APB. Okay, but here the nearest neighbor is not changing. And only the second nearest neighbor will contribute to the APB energy. So that is very important. So that also indirectly says that the displacement from X to Y in 100 plane do not alter APB, or the APB energy in 100 plane is much lower than the 111 plane. This is very important point to note. Okay, so that is what we are trying to understand from that. So what are the other important points? The slip system of the ordered structure is apparently stabilized by the dislocation behavior in the disordered state. For the Burgers vector of super dislocation is not the shortest lattice vector, which is 100 in both structures in V2 ordered alloy. So this we have already seen. So it's what is shortest lattice vector and translation vector and so on. But the requirement that the dislocation in superlattice travel in pairs separated by an APB provides strengthening mechanism. Very important. So what provides the strengthening mechanism in this alloys or in this kind of lattices? Okay, it raises because locking mechanism that affects the superpartial pair in the screw orientation. How do we understand this? Let us consider this to schematic. Schematic 1, what you are seeing is there are two superpartial screws, superpartial, which is just lying on 111 octahedral plane, and then you have the APB region and then bound by these two superpartials, and they are trying to glide on this 111. Okay, this is what is written here: screw superpartial pair with the APB on 111 plane, and the second one is trying to the superpartials which is on 111 trying to glide on to 100. Then what happens? This is what we have to see. Okay, what happens? If one of the superpartial is not dissociated, it can glide on a 100 plane. So we have to understand one point here. If you recall in the previous two slides, I keep mentioning that this superpartial should remain like this without dissociating further into Shockley partials. That is also possible, right? So if it is not dissociated, and then it can move on 111 plane, and then it can also glide on to 1000 plane, because in L12 systems 100 plane is also a slip plane. Okay, please understand that. The cross slip from 111 plane to the 100 plane may be energetically favorable if the APB energy is lower on 100 than 111, which is the implication of the simple geometrical picture of nearest neighbor coordination described above. So this is very clear. So when the glide can go to 100 plane, there the APB energy is lower, so that is energetically favorable situation. That's why it glides. Okay, but then there is a problem. What is the problem? Problem is, furthermore, depending on the elastic anisotropy of the crystal, the force one partial exerts on the other as a result of its stress field can enhance the stability of this arrangement. Okay, so whether it goes to the next plane, there are so many constraints. I'm saying that there are so many constraints. It's not going to just glide easily. Okay, we are yet to discuss the crucial constraint point. What is that? When the cross slip of this screw super dislocation on 100 plane occurs, glide of the remainder of the dislocation on the 111 system is restricted because the Pearl stress resisting glide on 100 is much higher than that of 111. So this is very interesting. We are qualified to understand this statement. We have now seen what is Pearl stress. What is Pearl stress? Pearl stress is a stress to move the dislocation in a perfect crystal. We have seen that. Okay, so that is more on 100 as compared to 111. So once the dislocation glide on 111 plane, and even though it goes to 100 plane, it gets stuck because there is a restriction by the Pearl stress. This is one aspect to look at. What are the other aspects? Thus, the applied stress has to be increased to maintain the plastic flow. So we are talking about plastic deformation here. Then only the dislocation will move, right? So the applied force has to be increased. So we are talking about how the dislocation mechanisms cause the increase in the applied load or yield stress. We are talking about that. So the 100 cross slip segment is known, this kind of a locked system which causes the more applied stress. This segment is known as Keir-Wilstroff lock. What is that? I will go back to this image now. This is much more nicely displaying that idea. So it is trying to glide to 100 plane, but then there is a restriction. So it get locked here. Okay, it get locked here. So this lock is called Keir-Wilsdorf lock. It's a very interesting point. Okay. The effect of temperature that results in the yield stress anomaly referred to the above probably arises from the case with which a of 110 superpartial can cross slip into 100 plane. So this could be the reason, this kind of a lock, or could be one of the primary reasons for the yield stress anomaly exhibited by these alloys. Very important point. Or we can also look at the other way. If it is dissociated into two 1/6 112 Shockley partials on 1 plane, it will have to constrict. Even if you think that, okay, we said that if the one of the partial superpartial is not dissociated, then it can glide. Even if it is dissociated into further Shockley partials of magnitude 1/6 112, it has to constrict and it has to narrow down by applied load in order to become a unit dislocation, then further. So these things requires energy, right? So that is an energy barrier for that can be overcome by the thermal activation. So that is why the high temperatures provide this thermal activation through which even if it is dissociated dislocation can combine to unit dislocation and further glide. This result is increased hardening due to cross slip with increasing temperature as seen experimentally. So this is all experimentally determined. Okay, all this hardening with as the temperature increase and all that experimentally observed. So these are the dislocation core mechanisms which is responsible for, which is at least believed to be responsible for the yield stress anomaly. So it also gives us a nice perspective of a dislocation in superlattices, how it behaves very differently as compared to the normal lattices. Thank you.